It's been a wild week with no school on Monday, and then more Atlas testing Tuesday and Wednesday, and now here we are having classes on Thursday and Friday. It's just chaos. What a way to end April, which today we end April. This is it. Tomorrow is the first day of May. We're so excited about that. Happy to see May here because that means, wow, the year is just about complete for school. So we are getting right there. I know some of you were with me at this testing this week, and some of you were elsewhere. But we were in Mr. Coffee's room up in Gateway, and he's like a history teacher, right? He teaches Gateway history and all of that. And all day yesterday, I kept looking. There was a box up on a shelf in the front of his room that said rulers. And so before I left, I just had to look because I'm like, okay, he teaches history. Is that a box that has little figurines of Napoleon and King Henry VIII? And no, there was no. I was disappointed. I'm like, rulers. Well, it was not. It was not. And actually, there weren't even any rulers in there. I think it's a box that used to be used for rulers, and now there was just like a piece of paper in there with like a paper clip or something. It's like, ah, it was lied on so many levels. No rulers, no rulers. Yeah, I just had to know. Just had to know before I left. It's like, surely. Hmm. We're going to be continuing our sequences and series unit. We looked at arithmetics, and I got a new, excuse me, I got a new interactive activity for us this morning. This is really cool. I've been playing with this. This is part of our training on Monday. I learned more. When I learned more about how to use this on Monday, I said, oh, I've got to use this in class this week. So I'm going to have that for you very, very quickly. We're going to do that one of the first things. But before that, let's see. Okay, I got that. Perfect. Let's see. I'm going to go ahead and pull our screen up here. Going to our grade screen, let's see where we're at. We're way down here. We've done arithmetic sequences and series. That's what we did last week. This week, we're looking at geometric sequences and geometric series, which they broke into two lessons. I don't know. Last week, it was all one lesson. This week, it's two lessons, but we're going to get through them both here. Geometric sequences, geometric series 7.02. So let's go take a look at this. And it starts out with this activity, which I have now provided differently. All right. In the chat, I'm going to put this link. All right. Everyone go to the chat, click the link. And this, you'll be able to just write the answers on your screen with your mouse there. Once you click that chat link, you may have to log in to Brisk. I don't know how that works on your side. Sign in with your school account there. It's the first time I've tried this with a class, so I'll be interested to see exactly what it looks like on your side there. Yes, you want to join my class when you get to that screen, by the way. Yes, join that activity that I created. And it will put this up on the screen, and you just write your answers on the bottom of the screen. And then when you write your answer up in the top right, you'll see check work. So, good. I got it on my screen too. So when you click on that link, you'll see something like this. And you put the answers there. I'd already started this. I want to take out my answers. Just like write down your answers. All right, some of y'all are getting it, but it's there in the chat. Make sure you click on the link in the chat. You can also type. Over on the right-hand side is your little toolbar. You draw or type. You can type your answers if you want to click over to the type. Yeah, so you can draw, you can type, however you like to do it. Okay, this is a geometric series. This is different than our arithmetic series we were doing last week. Just click that check work up in the top right corner after you put your answers in there, guys. Top right corner to check your work, and it will give you feedback. See, mine's not finished. Let me finish mine on the screen here. 64, 256. And it will check your work. It uses AI to check your work for you and then gives you feedback. All right, several of you are finished. Let's give it another minute or two. Some folks still working on it. Like I tried writing up here and it kind of went, whoa, it didn't want to let go. It does have an eraser over there too. But, you can erase things. But click that check work button when you're done. All right, if you're still working on that, you might want to come back and check out the lesson for now and leave that tab open where you can come back to it, try it. Kind of cool. The same activity that's right here on the first page of our lesson. Find the next three terms in the sequence. So, 64 and 256 and 1024. But instead of just telling you for right or not on here, that AI gives you feedback on what I did on that. So we're going to skip this right there. But our essential questions we're going to learn: how can an expression or process be determined for a geometric sequence? What functions combine to create an explicit formula for geometric sequences? And what possible restrictions exist on the domains and range, just like we looked at with arithmetic. Let's go to page 2 here. All right, this one we're going to do in the chat on the screen here. I don't have another activity built for this one. A geometric sequence is a list of numbers called terms which share a common ratio. Now, remember with arithmetic sequences, it had a common difference, but geometric sequences have a common ratio. All right, so if I make this a little bigger on the screen. So the question is this a geometric sequence or not? So we're going to put yes or no in the chat. So you just did some geometric sequences. That's what you were doing on that activity. You had to find the next three terms of the geometric sequence. And so you figured out, well, like the first one multiplied by 4, right? Every number was 4 times larger than the number before it. So this one, is this a geometric sequence? 4, 12, 20, 28. Now it is a sequence, and if this was last week's lesson, we would say yes. This is an arithmetic sequence, right? It's adding 8 each time, so that is not geometric. Good job. What about this? Is this a geometric sequence? 5, negative 15, negative 90, 270. Let's see, what's it multiplying by each time? Well, the first time it's multiplying by negative 3, right? 5 times negative 15, or 5 times negative 3 is negative 15. But no, that's just doesn't work. How about this one? 1126. Well, the fact that we go 1, 1, is it multiplying by 1 every time? If it is, how do we get to 2? No, there's something really wrong with that. There's not many geometric sequences here, is there? How about this one? Is this a geometric sequence? 7, negative 70, 700, negative 7,000. Yes, 7, negative. Yep, this is multiplying by negative 10 every time. 7 times negative 10, negative 70 times negative 10, 700 times negative 10. Perfect. What about this? 9, 45, 225, 1125. And some of these it's like, okay, I might need a calculator. So if I took a calculator here and I said 1125 divided by the term before it, Oh, that multiplied by 5. 225 times 5 is 1125. If I take 225 and divide it by 45, oh, that's also times 5. And we know 9 times 5. Oh, that must be a geometric sequence. Okay, it only gave us 5 of them. So some of them have patterns, but they're not geometric sequences. Some of them are geometric sequences. Good job in spotting the difference there. Now, just like we had with arithmetic sequences, sequences can be shown. Oh, move back up the page. There we go. Sequences can be shown in different forms. We were looking at lists of terms, right? 1, 3, 9, 27. But just like with arithmetic sequences, we could see it as a table where the n, the left column, the x column, is the term number. Term number 1 is 1. Term number 2 is 3. Term number 3 is 9. Term number 4 is 27. And if we can express it as a table, we can also express it on a graph as points. 1, 1. First term is 1. 2, 3. The second term is 3. 3, 9. The third term is 9. 4, 27. And again, you do not connect these lines because there's not a 3.5 term in between there. There's not a 3.9 term. So graphing it would mean it includes all these terms in between there, but there's not a term between 3 and 4. So not a continuous curve through the points. And again, we're going to, just like with arithmetic, we're going to find a recursive way and an explicit way to find terms. Recursive requires the use of the previous term, right? So if the first term was 3 and we wanted to find the second term, let's see, which sequence are they using? Oh, they're just saying 4 times a sub n minus 1. If the sequence went 3 and then you multiply times 4 each time, we'd say the second term is 12, and we multiply that by 4 and we get 48, and multiply that by 4, 192. And we find each term based on knowing the term before that. Based on knowing the term before that, you just multiply it by 4. But then there's also explicit, which allows us to calculate a term directly. Remember, like, this is great if we know the 4th, 5th, 6th term, but if we want to know the 50th term, we don't want to have to calculate every term all the way to 50. So we're going to learn how to get explicitly do that. So, all right. Deriving the explicit formula. We're going to work with this sequence right here. We're going to do it a lot like we did last week. Let's see, I'm going to write this at the top of the paper, get our notes started. Geometric sequence. All right, there we go. So the first thing they gave us was a sub n equals a sub n minus 1 times the common ratio, right? This was the recursive. If we want to know for a geometric sequence what the 5th term is, for example, we just take the 4th term and multiply it by whatever the common ratio. Common ratio. R is our common ratio. But how do we find, like, the 50th term of a sequence without having to find the 49th, which means we have to find the 48th, the 47th? So we're going to do it much like we did with the arithmetic. We're going to make a table to where we have the first term, the second term, and so forth. So remember last time we made this table here. We had the first term. In the second term, we just added the common difference 1 time. Then to find the next term, we added the common difference 2 times, 3 times, 4 times, and we was able to come up with a formula. Well, we want to do that same type of activity with, see, this is the term, with our geometric sequence right here. So I guess the first thing I got to figure out is what is the common ratio? R equals. Well, to go from 2 to -6, you're multiplying, well, 2 and 6 is multiplying by 3, but it changed to a negative. So it changes to a -3. -6 times -3 is a positive 18. Positive 18. So -3 must be our common ratio. So the first term is just going to be the first term. Oh, the first term is, it's 2 in this case. Looking at their sequence, the first term. So to get the second term, close our little graph there. To get the second term, we would take the first term and multiply it times r. Right? We take the 2 and multiply it times the common ratio, which is -3. I'll just leave it as r. 2 times -3 is -6. And to get the third term, we're going to take that 2 and multiply it times our common ratio. That gives us the second one. And if we multiply a common ratio again, that gives us the third term now. So -6, 2 times r is -6, times another r, we're at positive 18. And then we take 2 times r, which is this term, and multiply that times an r. And it just keeps getting bigger. 2 times r times r times r. That is this term. See, that's the same thing as this. If we multiply that times another r, that gives us the fifth term, which would be 162 as a positive. So looking at this pattern that's developing, r times r is r squared. R times r is r to the third, right? R times r times r times, that's 4 r's, so that's r to the fourth. So from that, we can see, hey, we've got a formula we can use. So a sub n, which would be any term over here, would equal the first term, 2, 2, 2, 2. That was the first term. So a sub 1. And what did we multiply it by? We multiplied it times the common ratio raised to a power. How do we find that power? We want the fifth term, it's 4. We want the fourth term, it's 3. We want the third term, it's 2. So it's the power of n minus 1. This is the explicit formula. So highlighting our two formulas for geometric sequences, geometric sequence, a sub n equals a sub n minus 1 times the common ratio, or we can just take the first term, common ratio raised to a power of n minus 1. So if we wanted to find the 50th, which is going to be a huge number, by the way, huge number, a sub 50, I don't know which one the lesson's going to take, but I'm going to take the 50th. I would use this because I don't want to keep going through every term. A sub 1 was 2. The common ratio is -3. And I'm raising it to the n minus 1, 49th power. Okay, this is going to be a huge number. This is going to be a really, really big number. So let's put our calculator up here and give it a good workout. 2 times -3 raised to the power of 49. That's a big number. I don't even know how to pronounce that because, see, this is, pardon me, thousands, millions, billions, trillions, quadrillions, quintillions. I guess that's septillions, I think. It's huge. -478,598. Yeah, I probably didn't want to go to the 50th term because I'm glad I didn't try to do this one by one. Okay, we're running out of room on that line. Okay, it's that really, really big number there. That's huge. Yeah, when you're multiplying by -3, it gets really big. And the next number would multiply that by -3, which would just keep growing exponentially, right? This is geometric is an exponential series. But that's the two formulas we need. So they go through and they say, there it is, multiplying by -3 each time. The fourth term is 2 times -3 to the third power, and that helped us find our formula. The 2 is the first term, the -3 is the common ratio. This is just going through what we talked about on paper. How's the exponent determined? It's the position of the term minus 1. And the fifth term is 162, which we found 162 on our chart. All right, so they're going to derive the geometric sequence and see if they come up with the exact same thing we did. I would hope so. But let's take a look.
The fifth term of the geometric sequence is 162. 162 can be written as 2 times 81. 2 represents the first term in the sequence, which is indicated as a sub 1. 81 is the result of 162 divided by 2. 81 can be written as -3 to the fourth power, where -3 represents the common ratio between each term of the sequence. 4 is the result of the exponential equation 81 equals -3 to the power of x. Use the variable r to indicate the common ratio. 4 is the same as 5 minus 1. 5 represents the fifth term in the sequence, and 1 is the difference between 5 and 4. The variable n is used to represent the position of the term in the sequence.
So yeah, he gets the same thing that we've got right there for our explicit. A1 R n minus 1. We built that going to the table. He just took the fifth term and worked backwards. But he ends up with the exact same formula that we had already written down in our notes. And there it is. A sub n equals a sub 1 times the common ratio raised to the power of n minus 1. And what do the variables mean? A sub n is the term you're looking for. A sub 1 is the first term. R is the common ratio. And then n minus 1 is just the same n that we used right there. You're subtracting 1 from it. So they used it to find the 11th term, which is a lot more reasonable than the 50th term because you just end up with 118,000. But you go 39 more terms, you get a huge, huge number. Okay. You may be thinking that the geometric sequence formula looks remarkably like an exponential function. You are correct. Like 3 to the x. F of x equals 3 to the x is an exponential function. Yes, because the variable is in the exponent. The n is in the exponent. So it really is an exponential function in there. So here are both formulas, the recursive and the explicit, that we already have written down our notes. I'll go ahead and make them bigger on the screen there so you can double check to make sure that's what you have. Common ratio times the term before it. I think I put the R second. You can put the R either way. So a sub n equals R times a to n minus 1, a sub n minus 1, or the first term times the common ratio raised to the power of n minus 1. All right. Let's move to the next page then. Page 4. It likes to talk about this combination of functions to where what you have here is a sub 1 is one part of our function. That is a constant, right? It does not change because the first term is always the first term. It only changes if you change to a different sequence. But when we're talking about a specific sequence, a sub 1 is always going to be the same number because it is the first term of your specific sequence. The r times n minus 1, that is the variable portion of our formula here because it's going to change every time you change to a different term. The n is going to change. The r will stay the same, but n minus 1 means it's going to change. So when we multiply these two together, remember with arithmetic sequences, we added those together to get our formula. With these, you multiply them. A sub 1 multiplied times the common ratio raised to the power of n minus 1. The domain and range work very much the same as arithmetic sequences. The domain is the x's. Remember when we looked at the table, the x column was the term number. Well, the term number, again, we don't have a 0th term. We don't have a 1.8th term. We don't have a negative third term. The domain is limited to all integers greater than or equal to 1 because the domain is the term number. And we have the first term, second term, third term. So that doesn't change. The range is not limited. It can be whatever, depending on your sequence, right? We saw negative numbers, we saw positive numbers, you saw fraction numbers in the assignment we did at the beginning. So the range is not limited. So let's do some example problems. Oh, and they like these. Find the 14th term where they give us the first and the 8th. All right, let's write this down. Both of these formulas, you'll notice, use the common ratio. We got to know the term. If we want to know the 14th term, we got to know the 13th term times the common ratio. And we don't know either of those things. We don't know the 13th term or the common ratio. This one, to find the 14th term, we got to know the first term times the common ratio to the 13th power. We don't know the common ratio, but both of them need that. But we do have two terms that we know the value of. So we can use this formula and work backwards to find r because we know what a sub 8 equals. A sub 8 equals negative 468,750. So a sub 8 equals the first term, which we know is 6, times r to the n minus 1. R we don't know, but we know it's being taken to the 7th power. Right? We know it's been taken to the 7th power. We got to work backwards to find what r to the 7th power is. So if we divide by 6, my 6 is getting a little lazy today. R to the 7th power will equal whatever this number is divided by 6. So let's find out what that is. Uh, 468,750 as a negative divided by 6. So this number is negative 78, 125. And that's what r to the 7th power is. Kind of wrote that above that, but that's all right. So how do we find what r is? Well, if you remember, if we have like x squared equals 9, and we want to find x, we take the square root because that is the inverse of squaring something. So x equals 3 or negative 3. Same principle applies here. If we want to know r, we take the 7th root. So if we take the 7th root of both sides, the 7th root of r to the 7th is just r. What's the 7th root of this? Well, on our calculator, see, this is the square root. But if we shift, it gives us a third root and a y root, whichever root we want. So if I have this number and I click this button, now it will ask me which root I want. I want the 7th root. So the seventh root is negative 5. So that is our r. R is negative 5. If we want to prove that to ourselves, we can take negative 5, raise it to the seventh power. And that is negative 78, 125. So that is negative 5 to the seventh power. So the seventh root is correct. All right, I'm going to put this over here. We'll need it back in a minute. Now we're ready to work our problem. The 14th term equals the first term, which is 6. The common ratio times the common ratio of, now we know what the common ratio is, to the power of n minus 1. N is 14. So 6 times negative 5 to the 13th power, and you can put that, if that bothers you. Oh, that's a terrible eraser on that pencil. If that bothers you, this is the same thing. You could put the 13 inside negative 5 to the 13th power. That's the same thing. I was just putting it outside because that's how we had our formula. So let's think. We'll start with the negative 5. Negative 5 to the 13th power. Let's do that first. And then multiply it times 6. Times 6. So it's a pretty big number, but the 14th term of this sequence is negative 7 billion 324,218,750. That's what we have for the 14th term. So let's see if they got a negative 7 billion number. So first you have to find R. So they go through the same thing we did, substituting A8, A sub 8, and finding that R is negative 5. And then to find the 14th term, they substitute it into the equation just like we did. And they end up with the negative 7,324,000,000, et cetera, number. So they like doing these problems where they'll give you 2 of the terms, but not in a row. They'll give you first and second term. And then you've got to find some other term down the line. Okay. A real estate developer is clearing 450 acres of land to build a commercial development. Every day, half of the existing land is cleared, which means if he wants to make money, you should be able to do it in 2 days. How many acres are left after 10 days? Now, see, he's not making any money because if they could do half of it in the first day, they should be able to do the other half in the second day. But they're getting slower because now they're just doing half again and half again, and whatever's left, they're only doing half of it each day. Where the last day, you got a guy that comes out there with a little spoon and just scrapes off some and clears the land. But what would be the first term of the sequence? Well, he's got 450 acres. So that would be our first term. 450. What is the common ratio? So it wants us to use with a fraction, a forward slash. So if every day half of the land is cleared, our common ratio is 1/2. Half is our common ratio. Now it says type your answer here. What is the value of the variable n? Well, they said after 10 days, how much is left? Well, that would be our n then. Must be 10 is our n. And then they want to know, using the formula, how many acres of land left after 10 days, round the solution to the nearest hundredth. And if there's a decimal, put a 0 in front of the decimal, if it's something like that. So let me write this down in our paper so we can put it in our calculator. This is the formula. The 10th day, we start with 450. The common ratio is half. And so n minus 1, 10 minus 1 would be 9. So let's pull out our calculator. Put these numbers in, 450 times parentheses 1/2. I can put it as a half in parentheses. It calculates it for me, 0.5, raised to the power of 9. So we have a little less than an acre. And they went to put a 0, 8, 7, 8, 9, 0, 6. And they told us to round it to what? The hundredths? Hundredths. That's 2 terms. So 0.88 then. That's it. Just using 1/2 as your ratio, 0.5. That works wonderfully. All right, here's our lesson summary for this. There's our 3 questions. Here's our geometric sequence formula. This one is the explicit. That's the same as this one right here. But there are the 2 formulas that you want to have in your notes, so you can use them on the assignments, the tests, the final, anything. The domain is restricted to integers greater than or equal to 1, integers only. The counting numbers, the natural numbers. The range is not limited at all. And you have a combination of the A1, which is a constant, and then the exponential function, which varies. All right. There are some practice problems for you on page 5. Identify the 10th term. So I'll let you practice those. There are 5 practice problems. Let's look at the assignment and let's get our other lesson out of the way here. Start. Find the 12th term, and I'll give you the 1st and 6th. Just like the problem we worked on paper. They gave us 2 terms, and you got to find a different term. Let's see. Same thing, 19th term. Here's the 1st term. Here's the 9th term. But you're going to work with a decimal this time because the 9th term is 358.8. Round the common ratio and the 19th term to the nearest hundredth. So when you take the 8th root or whatever of whatever number you end up with, round the common ratio to the nearest hundredth, and then use that to find the 19th term. If you don't get this number exactly, but you're really close to it, it's probably just a rounding thing. So go ahead and choose the one. You know, if you get 31,030.6 or something, you're off by 5. That's still closer to this than any of these other. It's just a rounding issue because when you round off, it's, you know, you could get a different number. So the bacteria culture begins with 13, which triple every day. Oh, every hour. They triple every hour. So how many grow during the 10th hour? Well, you've got your 1st term, you've got your common ratio, and you've got your A sub n. You can just punch these numbers into your formula and come up with that. Here's a function f of n equals 500. That's a constant. Here's g of n equals 9/10 to the n minus 1. That's a variable. Combine them to create a geometric sequence and solve for the 11th term. So do you subtract those? Do you add those? Do you multiply those? Or do you multiply these numbers and then raise it to n minus 1? That's a little different. And then find the 11th term. And here is a geometric sequence given to you as a table. 1st term, 2nd term, 3rd term. What's the formula for this sequence? And what is the domain? N is restricted to greater than or equal to 1 or greater than or equal to -4. 5 problems. Yes, I know I haven't turned it in yet. Let's look at the geometric series. Oh, they have a little, well, these silly little videos that they like to do. They're kind of entertaining, but they're a little goofy.
Rachel's mother just returned from a vacation to Moscow. She brought back a set of matryoshka, or nesting dolls, for Rachel. Nesting dolls are a series of dolls that open up so that each doll contains a smaller doll until you get to the smallest, innermost doll. The packaging that came with the dolls notes that there are 8 dolls and each doll is 10% smaller than the previous one. Rachel has a 2-foot long shelf in her room, but it's covered in small dolls already. She doesn't want to clear it unless she knows the nesting dolls will fit. First, she measures the largest doll. At its widest, it is 5 inches long. Rachel does not want to find 90% of 5 inches, then 90% of that number, and so on 8 times over. So instead, she uses a special way of adding numbers that change by a constant percent. The first doll is 5 inches wide. The next doll is 5 inches times 0.9 because it is 10% smaller. The next doll is 5 inches times 0.9 squared because it is 10% smaller than the previous doll. Rachel can find all of the doll's widths this way. She knows that when a number is multiplied repeatedly by the same constant, the sequence of products is called a geometric sequence. In this lesson, you will see how to add terms quickly in a geometric sequence. This sum is called a geometric series. You can use it to see if the nesting dolls will fit on Rachel's shelf. You find the sum of a geometric series using the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r. S sub n is the sum up to the nth term. In this case, you want 8 terms added. A sub 1 is the first term, and a sub n is the last term. So here, a sub 1 is 5, and a sub n is 5 times 0.9 to the 7th power. R stands for the common ratio and is the factor that each term is multiplied by. In this case, R is 0.9. So substitute and solve. The dolls will span about 28.5 inches, or just over 2 feet and 4 inches. Rachel's 2-foot shelf is not enough.
Poor Rachel. Man, loves that math. It just doesn't work. It doesn't work at all. Now, Rachel could move the dolls forward and back a little bit, can make some behind the others and probably fit. But she wants them to be exactly straight, and it will not fit in there. So what I took from that is he gave us a formula for a geometric series. Remember, when we have a series, we're taking a sequence of numbers and we're adding them all together. So a geometric sequence is the multiplying with the common ratio. So if we take those sequence of numbers and add them, that's a geometric series. So it's plus in between each one instead of commas. A sub 1 minus a sub n. So we have to know the first and last term, a sub 1, a sub n, and the common ratio. And this will tell us the length sum. Remember, S is the sum where we add them all together. So that's our first formula for the geometric series. But we have to know the first and last term. Okay, so a geometric series, similar to arithmetic series, is a sum of numbers. So let's look at these and put them in the category. Is this a sequence or a series? All right, we have a list of numbers. 1, 5, 25. Is that a geometric sequence or is that a geometric series? Now remember the difference. Series means we're adding them together. Sequence just means here are the numbers. So let's look at this first one together. A sequence or a series. This just has commas. There's the number 1, the number 5, the number 25. That is geometric. It's being multiplied by 5 each time, but it's just a sequence of numbers. Right? It's not adding them together. It's just giving us the numbers. What about this one? Sequence or series? Yeah, Braylon's right on top of that. Yeah, this is just a list of numbers. It again is just a sequence. Is this a sequence or a series? It's quick and easy to tell because if it's telling you to add the numbers together, that tells you right away, oh, this is not a sequence of numbers. This is a series of numbers. We're going to add them together. Now, this one's interesting. 9 minus 27 plus 81. And you might be thinking, wait a minute, that's neither one, is it? Well, what would the sequence of numbers be that they're adding? 9, negative 27, positive 81. It is adding them all together. It's just that the middle term happens to be a negative number. And when you add a negative number, you just subtract. So what would the common ratio be? Well, 9 times negative 3 would be negative 27. Negative 27 times negative 3 would be 81. So remember, geometric sequences can alternate between positive and negative. Because when you're multiplying by a negative number, you're going to have a negative and then a positive and then a negative, then a positive, then a negative, then a positive. This is a geometric sequence. So don't let that fool you when you see plus and minus, because you can do that when you're multiplying by a negative number as your ratio. Okay, we want to make sure we know what the definitions are. I need to make this bigger again. We have to know what these say. A sub n. Would that be the first number in the sequence? Would that be the common ratio? Would that be the sum total? What would they add up to? Would that be the number of terms in the sequence? Or would that be the value of the nth term? A sub n, that would be like a sub 11. That means the 11th term. That would be the value of the nth term, would be a sub n. A sub 1, whether we're talking about arithmetic, geometric, any of that, a sub 1 is always the first term, right? That's always the first number in our sequence. N is always the number of terms, N for number. R, we've already said R is the common ratio. And S sub N would be the sum total. What is it when you add them all together? What is the sum total? So if you're not sure about those, come do this exercise yourself. It's on page 1. Make sure you know what each of those stand for, what those terms mean. So let's find the formula for finding the sum of a geometric series. Take a look at the geometric series. 3 plus 6 plus 12 plus 24 plus 48 plus 96. And it wants to walk through here. Say, what is the first term? First term is 3. We can tell that. What is the common ratio between 3, 6, 12, 24, 48? We can see each time it's being multiplied by 2. This one's pretty. They gave us a simple one. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. Okay, the common ratio is 2. What is the sum? Well, we can add these together. 3 plus 6 is 9, plus 12 is 21. 21 plus 24 is 45. 45 plus 48 is 93. And 93 plus 96 is 189. So our sum is 189. We just add them together. But that didn't give us any kind of formula to work with. So they're going to have a video where we derive the formula with what we have already figured out from ourselves there. Apparently not. No sound. No sound on this one. So let's walk through it here. The first term is 3. So if we took a 3 out of every term, divide every term by 3. That's what they're doing first. 48 is 3 times 16. That's 3 times 32. So we said, okay, we factored out a 3 of everything. So the common ratio between each term is 2. So let's write all these as powers of 2. 4 is 2 times 2. 8 is 2 to the third power. 16 is 2 to the fourth power. So we'll convert all of those till 2 to the fifth power. So we've got a pattern that we can work with here. Each of those has a 3 multiplied by it. To find the formula, each term we need using variables. So we can change all those 3's to the first term and change all those 2's to the R. And we can see we've got a pattern definitely. Multiply both sides by the common ratio. So it says, okay, if we're trying to simplify this, if we multiply both sides of the equation by the common ratio, the r, we'll see what that does. That tells us that r over here, when you multiply an r over here, each of those goes up 1 degree, right? Let's see, they haven't multiplied on the right side yet. They just did right there. Each one goes up. R to the third times r is r to the fourth. R to the fourth times r is fifth. R to the fifth times r is r to the sixth. So multiplying r by both sides makes this to where every term has an r and it just increases each time. And the largest term is equal to the sum of the terms. There's 6 terms, and we've got an r to the sixth. But now we've got an r over here. So now they're doing something really interesting. We've multiplied r times both sides, so that's still equal. Now they're going to subtract the first line and the second line, taking the second line and subtracting it from the first one. This is something different. What happens there? If you subtract s sub 6 minus s sub 6r, they're going ahead and distributing that negative. Since we're subtracting, that means all of these would be a negative. And then we can just add them together. And when you taking these together, you've got an r here and an r here, a sub 1r and a sub 1r. When you're subtracting an a sub 1r, you have an a sub 1r there. Those will become 0. And you have a sub 1r squared, and that becomes 0. And a sub 1r squared, and when you subtract it out, those are 0, 0, 0. The only terms that don't zero out are the first term, and then you're subtracting this one. There's not an a sub 1r6, so it just leaves the first and last term. So on the left side, you've got s sub 6 minus s sub 6r. Over here, you got a sub 1 minus a sub 1r6. It's like, let's factor s sub 6. There's an s sub 6 in both terms. Factor that out. That leaves 1 minus r. And to get the formula for s sub 6, we divide both sides by 1 minus r. There you go. And that gives us our final formula. All we have to do is take the s sub 6 and just make that an n for whichever term we want. So for this term, we can use that formula. And if you look at that, interestingly enough, switch back here. That is the same formula we have written down. They just showed you the mathematical way to derive that from using a sequence of numbers, a series that we know. But this is the formula we had written down, and they just showed you mathematically how can you get that series. And you go through all of those steps to do that. Okay, page 2. Example 1. It's possible to use a geometric series formula. So find the sum of the geometric series, a sequence 5, negative 15, 45, if there are 11 terms. All right, we'll do this on paper. So we've got a sequence of numbers that goes 5, negative 15, dot, 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 and we want the sum of 11 terms. So let's see if we can use our formula to work this out. Sum of 11 terms. 5, negative 15, 45. Dot, dot, dot. So what is our common ratio? 5 to negative 15 to 45. We're multiplying by negative 3. What's our first term? 5. What else do we need to know? We need to know a sub 11. We don't know a sub 11. If we're substituting into our formula, s sub 11 equals, first term is 5, minus a sub n, we don't know a sub n, times negative 3 over 1 minus negative 3. We need a sub n. Well, fortunately, we have a formula to find a sub n. It's a sub 1 times r to the n minus 1. A sub 11 would be a sub 1, which is 5, times r to the n minus 1, which is 10. Right? That's our formula. A sub n equals first term times the ratio n minus 1. First term ratio n minus 1. So let's find out what that is. Keep this calculator hot today. Okay, 5 times negative 3 raised to the power of 10. So this is the 11th term. So we're going to need our calculator for sure on that. So S sub 11 equals 5 minus 295 to 45 times negative 3 divided by 1 minus negative 3. Okay, so we're taking a negative times a negative. Or we're subtracting that times a negative. 5 minus, and then we'll put in parentheses, 295 to 45 times negative 3. So that ends up 885, 740 divided by 4. So adding the first terms together equals 221, 435. And you might look at that and think, now wait a minute, that's smaller than our 11th term. Our 11th term is larger than the total. Yes, but you have to remember every other term is going to be an odd number that we're adding. So the term right before this was a negative number. So it's not going to be unusual that our total is going to be smaller than our last term. If our last term was a negative, if we took the 12th term, that would change because now our last term would be a big negative number. It would be this times negative 3. And this sum would be a negative, but probably not as big a negative. So what did we do? How can we fix our formula to be able to do a sub n? We took this formula, a sub n equals the first term times the common ratio to n minus 1. So we need to substitute that in to our formula. Let's do it down here first because we may need to simplify it. S sub n equals a sub 1 minus a sub 1 times r to the n minus 1 times r. Okay, so this is the a sub 1 r n minus 1 r to the n. I put it inside the parentheses just because we've got so many parentheses going on here. And all that's being multiplied times r. If we have r to the n minus 1 being multiplied by another r, now we've got r to the n because that moves r to the n minus 1 times another common ratio. That gets us to the next term. So these multiply together to be r to the n instead of the n minus 1. We've taken out the minus 1. It's not the term before anymore. Now we've got the next term. So our other formula we can use is a sub 1 And this is just a sub 1 times Rn minus a sub 1 times r to the n power 1 minus r. So with this formula, we only have to know the first term and the common ratio. It uses the first term twice. This one uses the first and the last term in the common ratio. This uses the first term twice in the common ratio. So there's our two formulas that we can use for this sequence, geometric sequences. I'll leave it up there a second. If you're writing that down, then we'll do some more examples. We'll play with it a little bit. Just make sure it's working right. We got about 10 minutes of class. See what else we got down. They do have two more examples right here. 8 terms of the first and last term. This gives you first and last term, so you can use the first and last term formula. And this one uses a different word problem. Viewership for the Summer Olympics increases 22% every 4 years. It says in 1980 there were this many. How many were there total between 1980 and 2008? And wants to know which formula you'd use. Well, you'd use the one that just uses the first term because we don't know how many there were in 2008. Submit. Excellent. And you can go through that. And it has you over here. Match up what term matches what. Yeah. N would be the number of Olympics. There's 8 of them in that period of time. The first term was 88 million and then 22%. So there you go. That's the two parts there. Okay, applications. Here's a bouncy ball, mega bouncy ball. Bounces 83%. That's 0.83. So he said the first time I dropped it from 3 feet tall. So the next time it bounced up, it was at 2.49 because that is 83% of 3. The next time it bounced, it was at 2.07 feet. The next time it bounced, 1.72. If he lets it ball fall 12 more times, boom, 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 boom. What is the total height that the ball dropped? Like here it dropped 5.49, add another 2, it drops 7.56, and just keep adding until you get 12 drops. And we can use our formulas. I'm going to go to the other problem. You can use this a sub 1 Rn. Substitute what you know in there. 16.75 feet. All right, I want to look at the lesson summary. I want to do a practice problem or two, and then look at our assignment. Here are the two formulas. S of n equals a1 minus a1 times r to the n. That you only have to know the first term and the common ratio. This one has the first and last term in the common ratio. Those are the two we have in our notes. That's what we need to know. Let's do a practice problem from page 3 here. Oh, this is matching. We'll this is all 4 formulas. This is pretty good to look at. I'm not going to take the time to match them all at the moment here, but I want you to look at this. This is all 4 formulas we've used last week and this week. Look, some of them are a sub n, some of them are s sub n. So you know a sub n is sequences, s sub n are series. So these are 4 formulas we've used. We've used 8 altogether, but this is 4 of them. So can you match those up? And I will leave that for you to do to see if you know which formulas go where. But you should have all those in your notes. So that won't be too bad. And here is 6 situations. And which one of these formulas would you use? Find the 6th term of 2, 12, 22. Which one of those would help you find the 6th term? That's arithmetic. 2 plus 10, 12 plus 10, 22 plus 10. So you need an arithmetic sequence, which means it's going to have a common difference, not a common ratio. So you want to use one of the common difference formulas. So that's a good exercise for you to do as well. But I want a problem to work here. What is the sum of this geometric sequence if there are 10 terms? All right, good problem for us to work here. So we need to know our common ratio. So we need to find the sum of 10 terms. The common ratio, to go from 4 to 24 and 24 to negative 144, you got to divide, go backwards. What is 24 divided by negative 4? That's negative 6, because the negative times the negative will make it a positive again. So that's our common ratio. We don't know the 10th term. We want to find the sum of the first 10 terms, but we don't know a sub 10. So dot, dot, dot. So we need to go use this formula that just uses the first term, because we know the first term and we know the common ratio. So that would be a sub 1, and I'm going to write the formula again down here, minus a sub 1 times r to the n 1 minus r. So the sum of the first 10 terms would be negative 4 minus minus of negative 4 times r to the nth. So r is negative 6 to the 10th power. Got to write all those negatives down to make sure I don't miss anything. I'm subtracting a1 times this. And since a1 is also a negative, I'm subtracting a negative times r is a negative, this 10th power, all over 1 minus. This is the only place it gets tricky. You got to make sure you don't lose track of your negatives. So it really helps to put them in parentheses. So let's find what negative 6 to the 10th power is first. Negative 6 to the 10th power. Negative 6 raised to the power of 10. Okay, so this is S sub 10. We'll simplify what we can. Negative 4 minus negative 4 times this big number here on our calculator. 64, 66, 176, all divided by 1 minus a negative 6. If we're subtracting a negative, we're adding. So that's all going to be divided by 7. Okay, let's take the next step and let's multiply these two together to know what we're subtracting. So S sub 10 would be negative 4 minus. And now let's find out what that minus is. So, okay, that number I've already got on my calculator right there. So I'm going to multiply it times negative 4. Now it's even bigger. So it's a negative 241, 864, 704. And I'm subtracting that negative. Subtracting the negative, which means I'm adding that to negative 4. So I'm going to add a negative 4. And now I've got this. And it's all being divided by 7. So the sum of 10 terms is this combined is negative 241, 864, 708. And dividing by 7. And let's see what it is. Oh, is it supposed to be a decimal? Is that one of our choices, or did we mess something up? We messed something up, or did they round it? And we're negative 6. 60, 476, 176, negative 241, 841, 704. Oh, somehow I see where I'm off. When I added a negative 4, they got 700. So I went the wrong direction on there. It's not 708, it's 700. Did I mess something up on that? Minus a negative. No, it sure went to a 700. I did something wrong on the calculator. It'd be 700 because I'm 4 would come off of that because that becomes a positive. Does that become a positive? It does become a positive. minus a negative. So this becomes a positive. And then I subtract 4 from it. There's what I did off. Okay, now let's take that number and make sure we got what they got. Let's see. 241, 864, 700 divided by 7. That's it. So I say, got to keep track of all these negatives, and I let my negative mess that up. 552. Check our work. That's exactly what they got. All right. Here's another sequence if there's 5 terms. Check your answer. Sum of an 8 term. The first term is -9. Last term is 703, 125. Common ratio. That one, you can actually use the first formula because you know the first term, the last term, and the common ratio. First term, last term, common ratio. All right, let's look at our assignment. We are out of time. Find the sum. There's 7 terms. You know the first term, but you don't know the 7th term. Evaluate S of 5. Here's the first 3 terms. They want to add the first 5 terms together. First 5 terms together of this sequence. Here's the yo-yo. It comes back up 60% each time. 0.6 is your common ratio. After 10, S sub 10. And then here's a graph. This represents the amount of bacteria for a colony that doubles every hour. This would actually be appropriate to put that in there because there is every hour between hour 1 and hour 2, they would have about that many in there. But what is the diameter of the bacteria after 9 hours? So the 9th term. All right, guys. Geometric. Fun stuff. All right, we'll see you guys on a normal Tuesday next week. So have a great weekend. You got two assignments, 5 problems each. Let me know if you got problems. You can send me an email, but we'll catch you next week.